Welcome to the deep dive, where we take a massive stack of sources, extract the most important insights, and deliver the knowledge you need fast. For a long time, machine learning felt like this, internal, almost academic thing. You'd build a model, run an analysis, and that was kind of it.
Right, it was confined to a notebook.
Exactly. But that world is just, it's gone. ML is now the live engine behind the services we use every hour. We're talking real-time spam detection, search engine filtering, those recommendation systems that update the second you click on something.
That's a huge shift. And it's not just about applying a model anymore, it's about competitive advantage. If your model takes all night to update, you're already behind.
So what's our mission for this deep dive?
Well, it's really twofold.
Yeah.
First, how do you deploy a trained classifier for a live service?
Yeah.
And second, and this is the really crucial part, how do you enable continuous real-time learning so the model's always getting smarter?
Okay, that is a big goal. So let's unpack it. We've got sources on big data strategies, the specific online algorithms you need, and then the actual tools for putting it on the web. We have to start with the biggest roadblock, the thing that changes the entire approach, and that's just scale.
It's always scale.
In a production environment, you're not dealing with 100,000 samples. The sources are clear. We're in the world of terabytes, petabytes even.
And you just can't load that into memory, not on a single machine. The whole process would just collapse before it even starts.
So since most of us don't have a supercomputer in the basement, what's the solution?
The solution is to think incrementally, and this brings up two really key concepts: out-of-core learning and online algorithms.
Okay, let's break those down. Out of core.
Out-of-core learning just means you work with the data without ever loading all of it. You fit your classifier piece by piece, feeding it these small, manageable batches.
And online algorithms are what make that possible.
Exactly. They're built for this. They don't need all the training samples at once. You can just keep feeding them new data over time.
And I saw in the sources, if you're using a framework like scikit-learn, there's a telltale sign, right? A specific method.
That's right. The partial fit method.
Yeah.
If an algorithm has that, it's your signal that it can learn incrementally. It can update its state without seeing all the old data again.
So it's a huge architectural trade-off. You're giving up the certainty of seeing every data point at once.
For agility and speed. And to make that possible, you need a very specific kind of engine running under the hood.
Right. And that engine is stochastic gradient descent, SGD.
That's the one. It is the absolute core of most large-scale online learning.
So for our listeners who might be familiar with standard gradient descent, how is SGD different, and why is that difference so important here?
The difference is all in the sample size it uses to calculate the error or the gradient. Standard, or batch, gradient descent is exhaustive. It looks at the entire training set to calculate the gradient before it takes one single, very accurate step downhill.
Which sounds incredibly slow.
It is very stable, but very slow. SGD, on the other hand, is rapid and a bit noisy. It calculates that gradient using just one data point, or maybe a tiny mini batch.
Wait, one single data point. If you're only using one sample, that gradient must be all over the place. It could be pointing in completely the wrong direction.
It often is. That's the core challenge. The individual steps are chaotic.
So how does it ever find the right answer? How do you stop it from just bouncing around randomly forever?
Well, that's where the magic is. Over many, many iterations, the average of all those noisy, chaotic steps points in the right direction. And you manage that chaos first with the initialization. You just start with a random guess for the weights.
Okay, a random starting point.
But the real control knob is the learning rate. This is a hyperparameter that scales the size of each of those little chaotic steps.
So if the rate is too large...
You'll just overshoot the minimum loss over and over again.
Yeah.
The whole system becomes unstable. If it's too small, well, it'll take forever to get there.
So the learning rate isn't just about speed, it's about taming the noise.
Precisely. And in production systems, you'll often see a decaying learning rate. It starts out large to move away from that random start point quickly, and then it gets smaller over time to let the model sort of gently settle in.
A controlled chaos.
A controlled chaos, exactly. And of course, you manage the process itself. You shuffle the data to avoid bias, and you have your stopping criteria. You stop when the model stabilizes, or after a set number of passes, or epochs.
And the sources use this for a movie sentiment analysis model, right? Training a logistic regression model with an SGD classifier.
A perfect example, because sentiment on social media, for example, changes constantly. You have to be able to update your model on the fly.
Okay, so we've solved the problem of updating the model's weights. But now we hit the next wall, the text data itself. If you're processing petabytes of documents, standard tools like Count Vectorizer just won't work right.
Correct. Because they require you to build and hold the entire vocabulary, a complete dictionary of every unique word, right there in memory.
And that dictionary alone could be huge.
It could crash your system before you've even started training.
Right.
It's the next bottleneck. We need a way to extract features that is totally memory independent.
Which brings us to the specialized solution.
The hashing vectorizer. Its big advantage is that it never builds or stores that vocabulary list. It gets around the memory problem using something called the hashing trick.
The hashing trick, how does that work exactly?
Uses a one-way math function. The source mentions the 32-bit murmur hash 3 algorithm to map words directly to a fixed number of slots or indices.
Like buckets.
Exactly like buckets. You decide ahead of time, say, I want 100,000 features. Then every word that comes in gets hashed and thrown into one of those 100,000 buckets. Your feature space is always the same size, no matter how many unique words you have.
Okay, that sounds incredibly efficient, but I see a potential problem. If you're throwing lots of words into a fixed number of buckets, some words are going to end up in the same bucket, right? Collisions.
You've hit the nail on the head.
Doesn't that mean you lose information? And lose accuracy?
That is the fundamental trade-off.
Yeah.
It's absolutely a trade-off. The sources are clear on this. The training time is much, much faster, which is what you need for online learning. But the accuracy might be a little bit lower than what you'd get from an exhaustive offline method with grid search.
So for something like spam filtering, where you need speed and volume, it's perfect for, I don't know, detecting a rare disease from medical texts. Maybe not.
Exactly. The operational benefit of speed outweighs the small statistical cost. It's what lets you do things like, as the source mentions, immediately retrain your model on those 5,000 test samples to make it smarter on the spot.
Right. So once we have this model trained with SGD and the hashing vectorizer, we obviously don't want to have to retrain it from scratch every time someone loads the app.
Absolutely not. You need to save its state.
And how do we do that?
We use serialization. Specifically, Python's built-in pickle module. It basically takes your complex Python object, the train classifier, and converts it into a compact bytecode format that you can save to a file.
And then when the app starts up, you just unpickle it.
You unpickle it, it loads right back into memory, ready to go, with all its learned knowledge intact.
That persistence is obviously critical for production. But we should probably add a quick note here. Pickle is convenient, but there can be security risks, Wade, if you're unpickling data from an untrusted source.
That's a very important point, a vital point, actually. Our sources are focused on pickling a model you trained yourself, but in any real-world service, you have to be extremely careful. Only unpickle files that you trust and that you generated yourself.
Good clarification. Okay, so we've covered the data problem, the algorithm, the feature extraction, and persistence. The last piece is getting this thing live on the internet.
Right. Moving to the web infrastructure. Our sources lay out a path using Flask, which is a very lightweight Python web framework, and pairing it with Gunicorn, a production-grade web server.
And Gunicorn is important because Flask's built-in server is really just for development, isn't it?
It is. It can't handle the kind of traffic a real web service gets. Gunicorn is designed to handle many simultaneous user requests, which is exactly what you need when you deploy to a cloud platform like Heroku.
And the sources walk through a few demos, but the key one seems to be the movie classifier with update app. That one isn't just a static model, is it?
No. That's the whole mission realized. It's a live app that can make predictions, but it can also take new data from a user and, using that partial fit method, immediately update its own model. That's continuous learning in a live environment.
So to get this whole thing, the code, the pickled model, the web server, onto a platform like Heroku, you need to give the platform some very specific instructions. What are those essential files?
There are 3 non-negotiable ones. First, requirements.txt. That's just a list of all your Python dependencies. Flask, Gunicorn, scikit-learn that the server needs to install.
Okay, that's standard.
Second, runtime.txt, which just tells the platform which version of Python to use. Super important for reproducibility.
Got it. And the third?
The third is the most critical of all, the proc file. It's short for process file, and it's the one command that tells the platform how to actually start your web server. It tells Heroku to fire up Gunicorn and point it at your Flask application.
And this brings us to that one perfect piece of insider knowledge from the source material. The tiny little detail that if you miss it, will cause you hours of pain.
Oh, yes. The single most frustrating, non-obvious detail. As of when the source was written, at least.
Go on.
In your profile, in the command to start the server, you must have a space before the word Gunicorn. If you don't, the app won't launch.
A catastrophic failure averted by a single space character. It's always those little things in deployment.
It really is.
Yeah.
So to kind of synthesize this whole journey for you, we started with a massive data problem, right? Terabytes.
An impossible problem.
It forced us to abandon batch learning and adopt an algorithmic solution, SGD, and out-of-core learning. We used the hashing vectorizer to handle the text without running out of memory, saved our work with pickle, and then packaged it all for the web with Flask and Gunicorn.
What this all really means is that these systems are they're fundamentally different. They're not static models anymore. They are living, adapting entities that are constantly getting smarter right there in the production environment.
But that agility comes with that trade-off we mentioned. And that's really the final thought we want to leave you with. We know that these online algorithms are a little bit noisier, maybe slightly less accurate than the big, slow, exhaustive methods.
Right.
So this raises a really important strategic question for you to think about as you design your own systems.
Which is?
When is the massive operational benefit of speed and continuous real-time learning worth that small, measurable trade-off in statistical precision? How do you calculate the business value that outweighs the cost of a slightly less perfect model?
That calculation, that's what separates a good data scientist from an expert who can actually deploy. Thank you for diving deep with us. We'll catch you next time.